Hi, my name is Noric, Couderc, and I work at Lund University in Sweden with Emma Söderberg and Christoph Reichenbach. And today I'm here to present our work in progress paper called JBrainy Microbenchmarking Java Collections with Interference. So let's start with an example where I want to create a set of countries. So here, even though I know I want to create a set, I have different options. I can create a hash set, a tree set, LinkedHashSet, and so on and so forth. So the question becomes, which one do I choose? And the answer to that question depends on the context, how I will use my collection. So can we use the most popular one? Well, what we've seen in our benchmarks is that actually the most popular one are not necessarily the one that use the best performance. So here in this case, on this plot, you can see that on the x-axis we have the different collections we've tried, and I'm going to come back to this slide to explain it a bit more, but on the y-axis you have some measure of performance. And what we can see is that the ones that are in green, which are the most popular data structures, are not necessarily the ones that give the best performance. So it seems that there is a mismatch here, and that's interesting. Now, okay, so we can come back to our example and think, so how do I use my collection, which is highlighted in blue here? And we can think, okay, so if I know how I use my collection, which we call its usage profile, and I know each implementation class strengths and weaknesses, which we call the cost profile, then we can pick the right implementation. We can match both to get the best performance. So how does the usage profile look like? You can think of it as a distribution over the method calls, meaning that some methods are called more than some others. And once you have this usage profile which you can trace, then you can go on the internet and find a table such as this one, where you can look at the implementation and the operations you want to do, and they would give you a cost. And these tables can be derived theoretically or empirically. This is all very good, but knowing that one method is slow doesn't give you enough information if you call a whole bunch of methods on the collection. So maybe we need to consider interference between the methods called, meaning that maybe you can pay an additional cost when you call one method, and you will amortize this cost a bit later when you call another method. So you need maybe to consider the whole history to be able to take the right decision. How do we benchmark if there is interference? So there is an existing piece of work by Young and al. Called JBrainy, where what they did is that they generated a whole bunch of usage profiles. They run them, benchmark them with different collections, and try to learn from that. Now, in their paper, they generate a usage profile by assuming that the distribution over the methods is uniform. Now, what we can see on the right-hand side of this slide is two plots, and one of them is a real-world usage profile from a collection in the FOP benchmark, and the second is a synthesized usage profile using our methods. And what we can see is that in both of them, you don't have a uniform distribution. You have some kind of bias in the sense that some methods are called a lot more often than some others. And we expand a bit more on this model for usage profiles in the paper. Now, for the hardware configurations, we only tried it on one machine, and we plan to do it on more machines, and I'm going to come back to that. So now we've generated usage profiles, and we've benchmarked them, and what do we get? So what we can see here is on the x-axis, you have the different collections that we've tried, and on the y-axis, you have the number of benchmarks for which the collection was the best. So for instance, in the case of ArrayList, it has a pretty high bar, meaning that it was the fastest collection in a lot of benchmarks that we've tried. And this plot is quite interesting because it gives you an estimate of the probability of picking the right collection, even if you don't know what you're doing. So in the case of list, the situation seems pretty straightforward in the sense that ArrayList seems to be the best collection in the vast majority of cases. Now, in the case of maps, the situation is a bit more nuanced in the sense that TreeMap and HashMap seem to be give more performance in more cases than HashMap, which is very interesting. But you would still have to choose between TreeMap and LinkedHashMap. Now, in the case of sets, the situation is a bit clearer in the sense that LinkedHashSet seems to be better in the vast majority of cases compared to HashSet and TreeSet, which is also interesting. So now that we've seen that, we try to look at different... in the case of lists, well, ArrayList is pretty much faster across the board. So there's no method for which the situation changes a lot. There's no operation for which the situation changes a lot. So in the case of sets and maps, we can see that LinkedHashSet and LinkedHashMap yield the best performance improvement when you call methods which have an implicit traversal over the collection. And this makes sense because LinkedHashSet and LinkedHashMap, it's by design, because LinkedHashSet and LinkedHashMap keep a linked list of all the elements so that you can iterate through them quickly. Now, we can also see that you get to speed up when you call add and put, and this is a bit more interesting because calling add and put a lot usually involves an overhead where when you use LinkedHashMap and LinkedHashSet, because you have to maintain the linked list. But we also think that because our benchmarks are always mixed, you try different methods, then usually this cost is kind of amortized later. In the case of TreeSet and TreeMaps, you get the most speed up when you call clear a lot, which also makes sense because clearing a tree is very fast. You just have to null the root of the tree and you're done. Okay. So why does this matter? Well, our results indicate that popular collections are often not the optimal choice, probably because LinkedHashMap and LinkedHashSet exploit interference, which is interesting. Now, what did we do? So we discussed the issues at play when optimizing collection use. We introduced our methods of microbenchmarking collections, and our results indicate that the most popular collections do not necessarily yield the best performance, and that interference plays a role in collection performance. Now, in future work, we plan to investigate the reason for speedups a bit more, and try with more JVMs and more hardware to see if our results generalize, and try it on real programs to see if our model of usage profiles is correct. That's all I have. Thank you.